Then we're going to switch to a summary from Tony, and then in the afternoon we're going to have lunch here, and in the afternoon we're going to go through a variety of related projects from all over. So that's the plan, and then at the end we're going to try to summarize everything in a more panel-like fashion as well. So Chad, thank you.
Good morning, everybody. Thank you, Imre, and all the local organizers for inviting me. As I was saying, I reflected over lunch yesterday that this has been a very productive meeting in my mind, and when I first started coming to any of the meetings that were joint astronomers in LIGO, it felt like everything was just a lot harder. And now the meeting has gone well. I think we're all speaking similar language and have similar goals, and so it's quite nice to see this, in my opinion at least. All right, so Imre asked me to talk about future prospects for LIGO data analysis. I have tweaked the title a little bit to focus a little bit more on compact binary systems. There are other experts in the room who probably can add more stuff about other transients, and I think we'll have plenty of time in the panel. I'm not going to make it a very long talk, so I'll leave lots of time for discussion at the end. Also, I'm not going to talk too much about future. I'm going to tell you a little bit about the current state, sort of near-term stuff, and want to get ideas during the panel session for what we should really be focusing on for 2022 and 2025. All right, so I'll start with the obligatory past observations, but I won't dwell on 150914. I actually want to use GW151226 as a case study briefly to set how certain things happen. And sort of interspersed in some of this, I think it'll give you a sense of just the normal status quo improvement in data analysis between now and 2020. But then beyond that, well, I can speculate some certain things that could be useful from the data analysis side, but I'm hoping to discuss it more in the panel. All right, so one thing about GW150914, which is, I think, important and I think everyone knows, it was discovered in quote-unquote online. Like, it was discovered by one of these real-time processing engines. Specifically, it was one of a generic, what we call a generic transient search algorithm or a burst algorithm, and identified this signal within 3 minutes of the signal arriving at Earth. So that was pretty cool, because I mean, everyone was saying, oh, we're going to do this, we're going to do this, we're going to do this, and then it happened. And even cooler than that, in my opinion, is the second one, also discovered online. So the only two gravitational waves that have been confirmed were actually discovered as part of the real-time processing engine. Confidently, pretty clearly, and it kind of worked as it was supposed to. And I don't want to sound too cocky, because I'm sure we'll screw something up, but it was nice to see. And I think, it indicates that at least this part of the multi-messenger program, which admittedly is maybe kind of the first step, but at least this part seems to work okay. So
reasonably confidently, but not with the ultimate confidence. I mean, there is a distinction.
There is a distinction, not with the ultimate confidence, and I can talk a little bit about that. But certainly, if we're talking about, well, okay, this one's an exception, but this one, for example, would have saturated the minimum FAR that we're going to quote for these. So, yeah, I get that. Because the bar was so high for detecting gravitational waves in general, clearly, doing a very, careful offline analysis to get these to the 5 signal level was critical. I don't want to undersell that in any way, but I mean, this did happen, which is nice. Okay, so the future is dim. What do I mean by that? Well, so as we've already seen, the first gravitational wave signal, if you look at almost unadulterated strain data, so this has been band passed between 50 and 350 hertz, which is pretty broad in terms of what the instrument's capable of. The Hanford and Livingston time series data, as you're all well aware, essentially shows by eye the chirp at this time. It agrees well with general relativity. Gaussian-like residuals. We all know this story very, very well. I like to think of this, though, as, in many ways, the GW community's equivalent of looking up at the night sky for the first time. So if we went back into antiquity for astronomy, we might say, well, yeah, we looked up, we saw the moon, we saw stars, good for us. But we know, of course, this isn't the end, right? So this is us looking up for the first time, and what we see is amazing, and this is great, but we want to go deeper. And, subsequent observations, I think the ones that are going to matter incrementally more and more will, of course, be dimmer, or in our language, quieter. So it is, I think worth it to push to discover quieter and quieter events, not only offline, but also online. Have more opportunities for multi-messenger astronomy. And I will argue in my very biased CBC-centric way that this is, going to hinge pretty much on having accurate models and the best possible data techniques. Because this is hard, and we have to work hard at it. And like I said before, it's worth being diligent, because I think a lot of the things that we're going to be talking about are so rare in terms of multi-messenger astronomy that we might have a one per lifetime event, right? And so the difference is we detect one thing or we detect 0 things, so I think it's worth putting as much effort into this. Okay, so this is an awesome cartoon. And so the point this cartoon is making is the original signal was so beautiful, and you can clearly see it with GW151226. That was not the case, as Barry had already said. In some sense, it spoiled us, as he showed. In terms of relative to the noise, which is the red here, with about the same bandpass filter, I think, the signal that's buried in here, which is sort of indicated by this black, is not really visible by the naked eye. So we had this problem, which is, I had to, right? Like, it's so fashionable. I felt left out. So.
The parity is wrong.
What?
Parity is wrong.
Yeah. Well, anyway, so we have our haystack, which in our case is the detector noise. Okay, we've been saying this for years, and you can see this, right? Like, a lot of noise, not really obvious signal. We're looking for this needle. We don't know the size or shape of the needle, but I guess we know that it's metal, and so clearly the obvious technique here for the needle in the haystack is pull out the metal detector. It makes the problem much easier, and that's essentially what we're doing with our modeled searches. We're doing matched filtering. We have a clever way of pulling the needle out of this haystack, and this was important. So for this particular event, again, it was initially discovered online within 67 seconds, 70 seconds. And it was identified by a compact binary matched filter search, but it was not recovered in the generic transient search. It was just too long, too low amplitude to be a good candidate for that. And as Peter points out quite accurately, it was an offline analysis that came and really targeted this and proved that it was a 5 sigma candidate, but the initial false alarm rate was 1 per 1,000 years. So we were able to say, right in the beginning, this is kind of pretty good. So so it wasn't like we had no idea. This looked pretty good. And again, this really did require sort of the match filtering, the careful modeling, all of those sorts of steps, and that's important going forward, in my opinion. All right, I want to spend just really quickly letting people know how this works. As an opportunity, maybe it'll help frame some discussions later. We all know we have interferometers, in this case just the 2 LIGO ones, but eventually this will be whatever we have for a worldwide network. Right now, we take data at different observatories. The data is collected and calibrated within about 10 seconds. That's what the timescale was when this was discovered. I don't want to speak too much on behalf of the calibration folks. I've talked to some of them informally. It seems like, they can already potentially get that down to 3 or 4, and I think maybe a order of seconds reasonable by 2020. Sound good?
Yes.
Okay, excellent. Thank you. I won't make a fool of myself.
Oh, look at that.
Yeah, good. All right, so have a goal something like 1 second. We broadcast this data to central computing observatories. We want to bring all the data together so we can analyze it jointly between the different detectors. So we broadcast that in this case. In this particular one, it was the Caltech cluster. We spread it out. We fanned it out across a bunch of nodes using a similar technology to like internet radio. Like you just sort of spray it out and everyone subscribes to it and listens. So we have this data spread out over a bunch of nodes. That's where we can analyze it. That's important because we want to process 250,000 separate models in this case in parallel all at the same time. We don't know what template is going to fit best. And so if we want to have the answers as quickly as possible, they all get searched for simultaneously in parallel, so we spread it across a few computers. For this particular one, we had that processing done within about a minute. we're searching the full parameter space BNS, NSBH, and BBH.
So what is that number going to be in 2020?
You know, it's great that you would ask. I happen to have additional. Thanks, Imran.
110 is
Oh, crap, yeah, oops. All right, yes, good call.
Well,
So
it's
right
kind of
throwing
now,
some
physics.
fast.
You only need 600.
yeah, that's right. Yes, the
So
European
let
problem,
me
that's
ask the
it.
question that I asked before.
Of course, yes.
Is it clear that there is no overlap between these 600, between these 1 million models?
Oh, there's tons of
The-
overlap in this 1 million models.
So what does it mean if you have overlap? I mean that you have two different initial parameters, but they give you, because
Very
of some
similar.
orientation, blah blah blah, the same signal it errors.
Yeah, there's a ton of overlap. We do exploit the overlap. And in fact, this particular analysis that exploited that overlap, I could go into more technical details, but there is overlap, and we essentially optimize this whole process to try not to lose more than 10% of the events. And I could explain it in a lot of detail, but maybe if it's all right over coffee.
Yeah, two nearby templates are 97%.
Yeah.
I'm not talking about two nearby templates. I'm talking about two far away templates that are different parameters, but because of orientation, of distance, and so or whatever, I don't know the details, will eventually give you the same thing. So I'm not talking about two nearby
No,
templates.
we
I'm
take
talking
the
about
data, we take the degeneracy into account.
We do. Yeah. And it's tricky, and actually,
It's a geometric algorithm. The distance defined in the parameter space, and we choose templates very optimal. We can talk about it later.
yeah, it's actually it's pretty clever. It's a pretty interesting geometric problem, but probably more people would get into it.
there is distance in the parameter space, but there is a different distance in the template space.
In the template,
Yes.
I
But
didn't
you-
mean the parameter space. I really
The
meant
distance is
the
really
signal
defined in the
space.
template space.
Signal space.
Yes,
And it is, I cannot imagine that it be one-to-one.
it's not.
Believe me, we have spent 10 years doing it, and it is a
Longer.
beautiful algorithm, and it's actually now adapted by pulsar, radio pulsar searchers who have found new pulsars using this algorithm. Because it's so efficient, and it is the best you can do for a given computing resource. Anyway, I think we should. Sorry?
Is it an open code or?
Of course.
Yep, yeah. Yeah, and the techniques, I mean, I do think that we could talk later with people that want to design filter banks and things. The geometric techniques for it are pretty generalized at this point, so I think any of us can help with that. All right, so right now we're searching 600,000 models, like literally now. Of course, the detectors aren't running right this second, but that's what we're doing right now, and we've gotten this processing down to about 10 seconds. So if you add up these two numbers, our time to database is 20 seconds. By 2020, there's no way this isn't going to be millions. I don't know if it's going to be more than millions, but it'll be millions. we're going to push further. I've got the big O notation. We can't really get down to one, but, a few maybe is reasonable.
Chad, what fraction that millions will be templates closer, and what fraction will be enlarged parameter space? Yeah, you need more models because you look for more things, or you look for things more finely.
Oh, for this is assuming the same. That's a great question. This is assuming the same resolution, sort of. So part of this is the low frequency sensitivity will probably improve. It may not. If it does, that'll affect this. And presumably we'll try to include whatever new physics we feel confident can be done. And that basically puts. We could go arbitrary. We could use all the computers if we wanted to. And it would put some reasonable cut on incorporating new physics. So when I say millions, it's like, well, that's kind of a no-brainer. It's a natural evolution of what we can do now. It may be a lot more. All right, so again, these things go to the candidate event database, and so this is something that, we heard a great talk from Leo. Hi, Leo. We heard a great talk from Leo yesterday. A lot of the stuff that he talked about sort of picks up from here. We first sort of, this whole engine here is to find interesting bits of data, right? And once it's reported, then there's a rapid stylization, which is one of the things that Leo talked about. At the time, it was a little on the slow side. It took a little, like a minute and a half or something. But, consistent with how long this all took. So basically, similar timescales. Now it's down to, I think, a few seconds. So this is now no longer really a limiting step, and we're making all of this stuff faster. But the full binary parameter estimation, which is stuff most people like to show plots about, thank you, is done after the fact, and there are lots of great rapid estimates of this, as Chris Pancock could tell you about. But the full problem takes tens of thousands of hours of CPU, so you don't get posterior PDFs on masses and refined sky positions and stuff for hours or days or weeks or months. Mistakes we know we are making. So this kind of goes to your question, Savi. A lot of the detection pipelines neglect a lot of known physics. We make up for it by this parameter estimation step where we can do more stuff after we've identified unique things, but we're not considering anything that is not, we're only considering aligned spins, so the orbital angular momentum vectors of the black holes are spinning the same direction as the spin angular momentum direction is the same as the orbital angular momentum. We don't consider higher order modes, and we have literally no matter degrees of freedom whatsoever.
But it could be anti-aligned. It's important.
It could be
to say that
anti-aligned,
you-
yeah, parallel or anti-parallel, yes.
Yeah,
And to give you a sense of this is an exaggeration, but a non-spinning template versus a crazy misaligned high-spin template, there's a lot of modulations, changing phasing and duration that won't be captured. This is a little unrealistic because in general you can find one of these models that better fits the green, but still we are neglecting some physics, and for the really extreme system that's likely to introduce a selection bias at the first step. The real-time analysis also isn't doing a completely coherent treatment of the data. It's sort of semi-coherent. It's not doing the full Bayesian inference up front, which could be beneficial even from the detection perspective of removing selection bias. And we need to do a much better job with real-time data cleaning. There's a huge detector characterization effort in LIGO, but very little of it happens in real time. And that is limiting. And this has to be turned over. I mean, as much as I admire the people who do this, it has to be turned over to the machines. There's no way that humans can be involved.
So Chad, detector characterization is very useful for burst.
How
How
much is
useful
CDC?
is it for CDC?
So black holes, it seems to matter. Like for BNS, this may be not an issue at all, though I can't predict the future. I mean, things get really weird, right? Like things could, we don't know the noise until we see it. Like, someone will put in squeezing and who knows what the noise is going to be like. For now, I agree it's not a big deal for BNS. VBH, it was a deal. I mean, part of the reason why the false alarm probability for GW15126 was 1 per 1,000 years and not 1 per 1,000,000 years was because of the echo.
So how much signal to noise ratio do you lose if it's using spin?
If in really extreme systems, it can be 30, 40%. I think Ian Terry has some work on this. Depending on how you do the average and what input distribution, you can conclude anything from it doesn't matter to it matters a lot. It depends on how unkind the universe is at favoring these sort of systems. If the really extreme ones could be mixed. And the signal to noise ratio is not the only answer. So we lose some signal to noise, but it also makes our goodness of fit worse, which pushes it into a regime that looks more glitch-like. So it's a double whammy. It's not just SNR, which I could explain later. It's an important distinction.
This is very important because this is the way to distinguish between different progenitor models.
Yeah, absolutely.
And right now the data does not favor a model of spinning black holes which are aligned, which is, as I mentioned yesterday, very alarming that it is not. So misaligned events will be, at least you should know how does it influence the statistics of events.
Absolutely. Yeah, no, there's no doubt there's a selection bias. How strong it is depends on the actual population of the universe, but there's no doubt that there's at least some selection bias. Sorry, I don't know who was first. Go ahead, and then Chris. Oh, Chris, go ahead.
I guess I just want to emphasize that it should be emphasized that this is a selection bias insofar as how far away we can see it, because anything that goes above threshold in the search then gets handed off to a more sophisticated analysis that does look for these effects as far as we can model them. So really, it's just the really faint ones that are far away that the search would then not ignore, but downrank because it doesn't quite match the limited sorts of templates that we have available for the online search.
I agree with that at the 50% level, but you can actually, there is a double whammy. It's not just SNR.
I don't
There's-
disagree with you at all.
It's
But
chi-squared too.
I just want to emphasize the point that it's not that we don't look for these physics at all.
Yeah,
That we're
absolutely.
insensitive to it. It's that our searches are limited in some way, and that limits the rest of the hierarchy.
Yes.
So I assume you plan, when you incorporate all these million new models back to the archive data and look at the
Oh.
first rounds?
Yeah, I mean, I think so. It depends. I mean, like, if in theory, yeah, that'd be great, but time's limited, and if the detector is 200 megaparsecs by then, it's maybe irrelevant. But if it turns out that it's about the same, then it's worth going back and looking. But it's a good question. Certainly, when the date's public, any one of you could do
Doesn't make the templates public too yet.
it. The templates are public also. It's all everything's open source.
Already, yeah.
Yeah, absolutely. I mean, it's non-trivial to run it.
We're
but you can-
required to do that.
Crowdsourcing
so.
for that too.
Yeah. Brent.
I would just say, I think the equivalent is, if eventually we would be able to create what we call in astronomy volume limited samples, one where we sort of have we're confident with a high enough SNR where we can say, okay, if there had been, these spinning cases, that we wouldn't have missed them. I mean, for the events that are just on the threshold of detection, I mean, these types of events could have a big impact on the rates.
Yeah.
But once we have maybe dozens or hundreds of events, hopefully we can just do a cut. And then be confident that for subsample of the discoveries that we know the distributions. Is that something that you think would be possible?
Yeah, I think right now the answer to how big the SNR has to be is a little alarming. Okay, look, I mean, I'm talking about maybe a tiny sliver of the parameter space where we might be vulnerable at the moment.
Okay.
It might be somewhat irrelevant, but I suspect that extremely extreme systems.
Look,
Could
I
be an
think
issue.
this probably attracting more attention than it really deserves. In order to produce that kind of thing, you have to have spins greater than 0.9 or 0.99.
Yeah, it's pretty
Okay,
nuts.
so it's, and also mass ratios have to be large. And that means that our sensitivity is not so great. So we don't look for those, but the chance of missing it, well, it may be at some, I think Chad put the right words. If nature is so unkind that all the signals are there, then it's bad. But at the moment,
Yeah.
you don't know.
Yeah, I didn't mean to raise alarm by it. Just that we should be aware of these things, and if we have an opportunity to remove selection bias at some cost we can afford, we should, in my opinion.
Moreover, all the data is there. We go back and
Yeah.
look into all that when we have the method.
After 15 or 9, 14, you cannot say that nature is unkind.
That's true. All right, so let me just. Oh, go ahead.
Just one sort of analogous question about missing physics from the templates. At what level of eccentricity would you get a 50% reduction in signal to noise?
There are people, Ellie, or maybe you could, there are people in the room who could probably answer that question even better than I could. Why don't you take it?
I will talk about that.
Okay, there you go. Good question. Okay, I'm going to leave this. Actually, I'm going to go right to conclusions, because we can talk about advanced data analysis stuff during the panel. So I want to say that I think, personally, I think at least the groundwork for the multi-messenger effort, thanks to a ton of people in this room, is in really good shape, in my opinion. From the LIGO side, it doesn't mean that we can be complacent. We do require, accurate models, which people will continue to work on harder and harder and harder. We do require match filtering for events which are dim. And from the looks of it, NS and NSBH will be in that category. So this is going to be critical. Current techniques are good, but we've got room to grow. And in my opinion, this is worth a non-trivial effort for how much we've spent on facilities and people's time and stuff. We shouldn't skimp on this, because it really could come down to a once-in-a-lifetime event being detected because we go the extra mile or not. And so I think it's worth spending time on. That's all. Thank you.
Thank you, Chad. So Chad will stay here for the panel. One quick question though, since we started a little late, we could break for coffee now or after the panel discussion. How does the audience feel? Coffee now or coffee in 20, 30 minutes?
I would like to use the restroom.
Okay, so I guess, okay, so coffee in 20 minutes, we'll continue with the panel.